So I thought I'd just start by introducing myself. So I work for CCP-EM, as you heard about in Tom's talk yesterday, if you were in the main session. So most of my work is on the CCP-EM software suite itself, but I do also do some work with EBIC to help develop their rely on data processing pipeline. We're joined today by three panelists. We have Carlos Oscar Sorzano, Dmitry Teganov, and Matt Yadanza. Carlos Oscar, we saw chairing one of the sessions yesterday, but just to introduce him briefly, he's a professor at CNB, which is the Spanish National Center for Biotechnology in Madrid. He's technical director of the Instruct-Image Processing Center, where they develop software that includes XMIP and Scipion. Dmitry Teganov is a PhD student at the Max Planck Institute of Biophysical Chemistry in Göttingen. More recently, he's been working on pushing the resolution of single particle cryo-EM and subtomogram averaging in some quite impressive work, but more relevant for this meeting is that he's also worked previously to develop the WARP software for on-the-fly processing. And Matt Yadanza was previously a postdoc at Leeds, so where they're hosting this meeting today. He developed the on-the-fly processing pipeline that's used there. He's actually now working with us and me at CCP-EM, and he's developing new metadata handling and pipelining for Relion and CCP-EM software. With that, we'll start this session with a short introduction from each of our panelists. So I thought, if you're happy with that, we'll begin with Carlos Oscar.
So I see that automated pipelines can be used in two ways. One is for fast processing, and this is mainly for the facility feedback. So that just to get an idea of what are the current foci, if there are eyes, what is the approximate number of particles, things like that. And it is very important to have a monitor over time of these parameters. The other one is if you also want at the same time to do some accurate processing so that the user can continue and doesn't need to start from scratch. And I will focus more on this second part of having a very accurate processing. And for that, what we promote is that you need several algorithms because all algorithms make mistakes. And here you have different frame alignments with different algorithms, different parameters. And what you see is that the shifts that you get for each one of the frames might be slightly different. And then you may want to compute the consensus of all those frame alignments and make sure that the one you are producing is the right one. If you don't care, if you just want to produce a result and have a rough estimate of what is happening, then you don't care. You can use any one and be happy with the result. And the same happens when you pay attention to things like the power spectra, how is it behaving with frequency or histograms, that they're not all the same. And you need several algorithms to make sure that what one is computing is the right thing. And here is another example. So this is just a CTF estimation, a standard CTF estimation. It looked good on these tone rings. But if you require two algorithms to agree up to very high resolution, then you get much better results later when you do the 3D reconstruction. And the same happens with resolution. So for instance, resolution, all CTF programs report resolution, but there are other programs that report other things. And then for instance, XMIP CTF is reporting the CTF non-astigmatic validity. And this non-astigmatic validity is limiting actually the resolution in many projects. Even if you have energy at very high frequency, it doesn't mean that this energy is fully usable in a useful way. Then the same for picking. So if you just want a picking, you can apply any algorithm, get a rough idea of the number of particles you're getting. If you want really good, or the best particles you can have with the current algorithms, you need to combine several algorithms with deep consensus and micrograph cleaner. And this doesn't mean that necessarily it has to be slow, simply that you need you need more computational power to do this. So in conclusions, there are a few ideas I would like to throw in. So for instance, when you are doing automatic pipelines, there are automated decisions. So for instance, which parameters are correctly estimated, which micrographs and particles should progress automatically to the next step, and monitoring and reporting the correct fraction of all these things at the level of micrographs, at the level of CTFs, the level of particles. And if you want to do it very accurately, then you need to be flexible so that to compare the output of several algorithms, and you need some ways to combine those outputs so that the mistakes of one algorithm are not the mistakes of the other, and then taking an automatic decision of which ones of these parameters were correct. And that's it. So this is the work of many people in the lab, and I don't want to monopolize, so I pass it back to you, Colin.
Yeah, thank you very much for a nice introduction, Carlos Oscar. I think that sets the scene for our discussions very nicely. Next, we'll have a short introduction from Dmitry Teganov.
Okay, so my introduction is going to be a bit shorter. I only have one slide. So I'm a big fan of this pipeline, mostly because I wrote 2/3 of it, and as you all know, you never go beyond 2/3. So the part that is most relevant to you is probably the one between the microscope and the big W, which stands for warp. So for conventional 2D movie data, it's fully automated in Warp. Warp offers you all the pre-processing steps with motion correction, CTF estimation, deep learning-based particle picking. For a tilt series, it can also do all tomogram things, so like reconstruct full tomograms, reconstruct subtomograms, do template matching on tomograms. And then it can automatically export the particles, either 2D or subtomograms, which then go either into Reliant or Cryo-ERIC. But Cryo-ERIC doesn't have support for subtomo averaging, so Reliant is really the more comprehensive solution here. And there you can do all the classification and global alignments. And then as a kind of advanced particle polishing step, if we're talking about this in Reliance terms, those data can be exported into a new tool called M, which we released this summer, which then does reference-based frame alignment or tilt series alignment. Can also do this with as many different particle classes as you want, or as many as you can fit into memory. And then M produces either the final reconstruction, or you can reuse those refined alignments to go back into Warp. It uses the same data model, and especially in case of tomograms, using those improved tilt series alignments, you can probably do more with some more difficult particles in there that are not ribosomes. And the main idea for Warp was to make it as automated as possible if things work well, but if they don't, then Warp has a very rich graphical user interface that lets you really dive into all the individual micrographs and the individual CTF fits to figure out what exactly is going wrong.
Okay, great. Thanks very much, Dmitry. Let's a brief introduction from our third panelist, Matt Yadanza. Over to you.
There we go. Hello. One of the things that I'm working on at CCPM is tools for integrating Reliant into automated data processing pipelines. So this comes as a three-part package. The first is what I'm calling the pipeliner. So this is essentially a Python implementation of the scheduling and file management aspects of Reliant with a bit of improved error checking, and also a new plugin functionality, which I'm not really going to talk about today. Second layer of this package is a Python API, which allows access to all the higher level functions in Reliant through just a couple of lines of Python, and will make Reliant a much more scriptable program. And then a third, even higher layer is command line interface to easily run higher levels, again, from just the command line, and some interactive from command line job creation utilities. So an example of the code that you could use in this API, just a couple lines of Python, you can initiate a Reliant project, schedule jobs, and then run the schedule. So this will be kind of eminently scriptable, and you could use this in part of a larger Python program or script to have decision-making or other scheduling things occurring. So running programs from the command line is also going to be extremely simple. Here's the same example before, where I added 3 jobs to a schedule. and then ran the schedule. Again, all just done from command line with just the job.star files that Reliant uses as containing the parameters for all the jobs. And this again will be, you can just edit these files, or an outside program could edit these files. This would be scriptable. And this also has a bit of things to make it more user-friendly, such as intelligent parsing of job names, where the actual name of this job auto pick number 4 here, you could actually enter any of these other permutations of this job name and still get either the incomplete job name or its alias and still get the actual job. So here's an example of some of my early test data. This is an entire Reliant project from start to finish, run with just this much code on the command line. And I just basically I initialized a new project, ran the kind of pre-processing through class 2D as one schedule, jumped out, used the GUI to select some classes, ran through class 3D, again, selected my 3D classes, and then ran the whole rest through post-processing, polishing, CTF refinement, and a second round simply from the command line using this new interface. So right now, I'm currently testing this, and I'm making a beautiful modified version of the Reliant GUI that will have no real outside difference to the users, but we'll be running this so we can distribute this to some test sites and really test it and make sure there's no bugs or anything. And then in the future, I'm going to be working on integrating this into schedules based on feedback from previous jobs, expand this plugin system, which I'm talking about. Currently, I've written 5 plugins, 2 of which integrate 2 things that are already part of Reliant, the reconstruct and project commands, and then 3 for outside programs, so Cryo-EM, Cryolo, and 3DFSC from NYSBC. But this plugin system is still quite nascent and will probably develop a lot more as we go on. And in the long run, we would like to eventually produce a new modern GUI for Reliant, especially if there's going to be a new advanced scheduler, which is going to be more powerful. The goal being to make something that is powerful but still usable and simple enough that people can use it effectively. So I work now for CCPM, my colleagues there, and this work is supported by a partnership between Global Phasing Limited and MRC. So we have support from collaborating with Jira, Brooklyn, and Shores as well.
Thanks very much, Matt.
Yeah.
Okay, and thanks to all the panelists for interesting introductions and also for keeping it short and giving us plenty of time for the wider discussion. So I thought I'd get things going by asking everyone, as a kind of looking more widely than this, what are your experiences of the different processing pipelines you have? Any particular pros and cons, or an immediate wish list for things that are not addressed at the moment and you think could be done better?
I have a few things in the wish list. That one of them is including the atlas and measuring the ice thickness, and if possible, even talking to the microscope. For instance, you can use Cryo-EM and somehow drive the image acquisition in those areas where images are more likely to have the correct ice thickness and things like that. That would be great. Yeah. Also, I don't know about the rest, but the image acquisition is getting faster and faster, and then the processing is really and moving the data around is really becoming a bottleneck, and then well, that is another issue, especially for those facilities that have to process in a cluster, so they don't have a dedicated machine nearby the microscope, but they have first to move the data to a cluster, and then that is becoming very slow, and then recovery, that there are network failures, and then recovery from these failures and so on. It is putting some pressure on the programs and the pipelines.
What I want to say picks up exactly on the second point Carlos Oscar just made of if there's any way of standardizing, a way of moving the data from the microscope to the cluster. So Colin, you yourself helped with me trying to do that, and I got template scripts by messaging a few people, but certainly my problem is rapidly moving moving the newly acquired micrographs off to the cluster in a fast and sane way. And I feel like maybe multiple people are reinventing the wheel. And I know there's probably some institutional, specifically institutional things, you know, exactly how your network is configured. But I wonder if there's any way something like that could be put into these on-the-fly processing packages.
Yeah, I would very much like that as well. That speaks exactly to my experience as well, which is the processing itself is easier to automate and write software for, but everyone's network and data transfer system is different, and everyone seems to have their own custom-built solution, which is more or less hacky and more or less reliable. So yeah, if anyone has any ideas on how we can get to grips with this better, I'd be very keen to hear them.
Well, Colin, feel free to comment on you know our pipeline quite well. If you want to comment on how data is moved off our detectors to our cluster for processing by Relion, and your impression of how that could be improved or optimized, and then feel free. I think you've probably got quite a good window into that and how well that ties in with your pipeline.
My experience at eBic is actually not so good on that side, because I as a purely computational person, I never get my hands on the detector PCs or the microscopes. But as I understand it, you run an rsync bash script from Cygwin on the detector PCs that then pushes the files into the wider file system, and at that point I pick them up on the Linux side, and then I know what to do with them. But I think eBic solution is definitely on the more hacky side from what I've seen, but I don't know how it can be done better. So yeah, if other people have ideas or suggestions.
It's pretty reliable though. That's the one thing I know it's a bit hacky, but yeah, it is pretty reliable. We've had very little issue with rsync and moving files from the detector machines to the network.
Felix, you've had your hand up for a while. Did you want to say something on this topic or something different?
On both, actually.
Okay, great.
So first on the data transfer quickly, what we do at Amble, we don't write anything on the microscope PC. So for the case, we write the output, the images directly on the user storage, which helped a lot. And for the K2, it was not possible, so we are not using rsync. We are using the frame watcher command from iMod. And basically you just move from the Gatan PC to the user storage automatically, and also doing some on-the-fly pre-processing. But just a more general comment about just my personal opinion, what I like, so we are using iMod, so frame watcher, and also warp. And we like it because it's easy, because we can't choose it, but all the microscope PC, Gatan PC, support PC are Windows-based machine, and warp run on Windows. So we just download it, install it, and it works. I've seen many fancy suite software on-the-fly processing, but you need at least almost an IT team just to have it running properly, and sometimes just not possible. Yeah, that was it.
Just a quick question for me on that. Does that mean you have to upgrade your Windows PCs with GPUs and that kind of thing to be able to keep up with?
Yes, yeah. It's the support PC. On the K3, we are just using the K3 GPU because it's delivered with a fancy GPU. I think it's a V100 or something. It depends a bit, but so we run directly warp from the Gatan PC, K3 Gatan PC, using the Gatan GPU, and directly on the user storage. So it's just a question of internal network. And for the Cryo-EM with the K2, yes, the support. So on this end we run warp on the support PC, which has been upgraded, but not a fancy one. It's already 8 years or 6 years old now, but yes, needs a bit of GPU.
Thanks, Felix. There's a few more people with hands up, so I'm just going to go through them in the order I can see them on my screen. So Marcus, that means you're first.
Okay. My first comment on the data transfer is we basically have WinSCP running, and we're just limited by the connection speed of our glass fiber cables. So that program runs fast enough to not be the limiting factor. But we have the advantage that our IT computers are basically a few rooms in the other direction. So it's a rather short cable. But the question why I actually have my hand up is more on all the programs that you basically also described are about automating the actual processing process. But are you also thinking about basically integrating some kind of metadata analysis in it? Because also yesterday it was shortly brought up that a quick display of the metadata can be very, very helpful for user and also for the facility people themselves.
So is that metadata analysis something you don't have at the moment, but you would like in your system?
We have something homemade, so it's nice, but it's also a bit dependent on a postdoc, for example, which we're having. If that postdoc is gone, that development over there is either stopped, or we have to train somebody completely new on it. But if it's something which is centralized coming from people who are anyway developing this software, I think it helps us in terms of standardizing these things. And also, if I would think being a user coming from one place to the other, it would be kind of cool to basically have the same kind of feedback mechanism. And I know a lot of people basically stole from each other. They're basically a similar design idea. So I think a lot of people do want to do the same kind of thing.
What kind of metadata are you referring to?
I mean, for example, what we are collecting is ice thickness, because we also have a really beautiful energy filter, so it's very easy for us to measure. It's about CTF parameters, so what's the resolution of it, some other quality markers for motion correction, which we're constantly popping up, especially for motion correction. We have some graphs. They can basically track the motion during the frames. I mean, these would be the basics, but you could think about more and more in terms of, for example, where was my image good? Are there a certain amount of good squares or a certain amount of bad squares? If you use multi-hole, do you see a problem when you start using higher image shift versus lower image shift? So there's a lot of things I think you could kind of think about to extend these kind of things as well.
As far as I know, most of these automatic pipelines, they record all these kind of things. Maybe the most advanced, like empty holes or things like that, they don't. But the rest, normally they are standard.
But it's not only about the recording; it's also about the displaying. I wouldn't know necessarily about like a, what people want to have is like display my parameters or display my my summary of the data, and then not only have like I mean, I can make a display of motion core and I get everything from motion core. I can make a display of CTF and I get everything from CTF, but like to have a ground picture, this is everything from one image, all the information recovered from all the different steps of the pre-processing, especially.
We do have that. Yeah.
I know that, but that's basically the question is would it be ideal or sensible to invest time in organizing that on top of your efforts that you're already doing, basically?
Just to comment on that, Warp has that. So it compiles most of the metadata types that you mentioned in one big overview plot, and the parameters that are not compiled there are all stored in XML files per micrograph. So if you wanted to make something more custom, you could also easily parse those.
That's also included in the scope of the project that I'm working on is metadata capture. So I'm interested in what metadata people are really interested in, because we're talking about from that end of looking at, during acquisition all the way through, once you've processed, wouldn't it be easy to have a essentially one-click deposition to EMDB rather than having all the metadata from your entire processing stored and available in one place. So I think this is something we're really focused on and interested in what data they find especially useful.
Okay, maybe people can put specific things like that in the chat so we can keep this discussion going. I think it's time we move on with the people with their hands up. So Christian, you've been there a while and you're next to my list, so go ahead.
I just want to add to the data transfer and using Warp. So we have, since all the support PCs for the cameras, like the offload data server for the Falcon camera and the Gartan PC, they're both running on a Windows server. And we actually just use a PowerShell script, homemade, which is start, and then you just type in 5 different parameters, which is like source, destination. And if you're able to mount your file server as, for example, an exported Samba share or something, then this is very, very straightforward to use. And we use it to actually just move the images as they come in, and then we usually run Warp either on like a distal machine, or in case of the K3, we also run Warp on the K3 server directly. And I think it's only a 10G line, that's connecting our K3 server to the file servers. And this is sufficient if you don't collect in super resolution with tons of frames and you have 2000 particles per field of view, then the processing speed can easily keep up with the microscope in our case. So this is a very, let's say, straightforward and easy solution, because I think the servers, they also come with PowerShell already installed. So you just take the script, you start it, and it works. The only thing that we needed to manage is that we can actually mount the file servers on the Windows machines as network drives. But this, the local IT should be able to do this, I think. Oh yeah, and the moving script is on GitHub. So on my GitHub page, you can download it if you want.
Okay. Next up with the hand is Dovile. Do you want to say something?
Yeah, I just wanted to comment on the people that some people really find it's an advantage, you know, to have warp on Windows machine, but we see it opposite. So the problem is, so personally, I really love warp, and I mean, we used to use it a lot, but now I'm talking about from my experience at the Max Planck Institute of Biophysics. The point is more and more people starting to use now CryoSpark. It's just because of our system. Processing CryoSpark is just so much faster because we create a cluster for that. And, you know, for warp, we have just a single machine. And it just cannot catch up. And we have also several complications with the way the data is being processed, because in our system, so we always need to store the raw data in one folder where it cannot be touched. So we cannot do any direct processing in that folder. So all warp processing need to be done on another folder. So what we do, we always link images to another folder. But the problem is with those linked images and warp, typically it does not update. So as soon as you linked it, so it doesn't see the new upcoming images automatically in warp. So we always need to stop warp and then to activate it again, and then it sees newly coming images. But it's, so it comes, for us, it comes again semi-automatic, not really automatic way of on-the-fly processing. And this is the reason why actually now more and more people in our lab, they're starting to use CryoSpark Live for that, because it's just then everything is more automated and then everything is on the cluster. And it's easier for them, even though still, you know, some of the selection features and other things, the simplicity of turning to rely on from warp, I really prefer. But that's why we're also discussing if we could, if it would be actually on Linux and we could also implement into the cluster and the system that we're using. For us, it would be easier, you know, to use warp, but just a comment.
But do you mean that people are already using CryoSpark Live at the Max Planck?
Yeah, exactly. So I mean, a lot. So I personally do both. So I actually start actually at the same point, at the same time I start CryoSpark Live and I start warp, because CryoSpark really gives me 2D classes very quickly. So the output on our system, the way we run, it's so much faster. So I mean, yeah, I get 2D images very, very quickly. But then actually what I get from CryoSpark, this I can actually really use for my further processing in Relion. And this is what I typically take. Because yeah, basically in CryoSpark, I don't get such good results, and yeah, but these are another, I think, preferences about the software and, you know, processing. It depends from project to project, and yeah, but yeah.
Okay, thanks. Dimitri, do you want to comment on that at all, since the warp came up a lot there?
So the chances of warp being ported to Linux are very slim at the moment, because it would be a huge amount of work, and I would not be able to handle it myself at this time. And about the different input and output folders, this is indeed a very early design decision that I've come to regret, but this is also a product of the environment in which warp was developed, which Christian has just outlined. Basically, we never had to separate input and output folders. But this will most likely be available rather sooner than later.
Next person with a hand up that I can see is Yuri. Do you want to say something?
Yeah, it's pretty, I mean, early in conversation, Carlos mentioned that he would like to have ice thickness estimation. So we have icebreaker program, which we currently integrate into Relion. Hopefully will be released by the end of the year. It doesn't give you absolute value, but you can internally calibrate it in the lab, and it will give accurate enough value if camera is gain referenced at the same the same value of electron per pixel, it should be quite accurate reading. It also helps to remove gradient and hopefully will help particle selection, because you can just eliminate some ice contamination as thick ice, and you can just deselect this entire group from further processing. So it could be quite interesting, and hopefully it can be developed further to be linked to target selection, but that's something for the future. And the other remark, I think me and Dan, with our scientific computing, are currently involved into basically mostly it's done by scientific computing and other Diamond resources. We're integrating a lot of metadata into IceByB. So the idea would be that we have a database of metadata which you can use, and hopefully it will also useful. I know that IceByB was initially designed as a database for synchrotrons, but I think Cryo-EM now approaching stage where we generate as much data as, well, close to as much data as synchrotron could generate. So potentially, I think IceByB, I don't know, just an idea that might be more widely adopted by EM community in the way of storing and then managing the data, and hopefully transferring to data storage like Empire.
Yeah, the SRF is also using IceByB for all this metadata acquisition, and it is also integrated with Cytium, so that we report back some of the parameters they record. They use it normally. I don't know at EBIC. At EBIC, I don't think they do. And that was a project of producing kind of light IceByB, so that anyone could use it in their facility.
Next hand up I can see is Felix. Do you have something else to say?
Had a rather specific question, general question. How do people handle the Falcon 3 data that ended on the Falcon 3 server? Because at the moment we have a rather utterly inefficient pipeline where we have no pipeline. People are just coming the day after to transfer the data on their own storage. So I was curious to hear if people had a nice, cheap, easy to install setup to do at least some pre-processing and on-the-fly processing, maybe directly on the Falcon 3 server. Curious to hear what people are actually doing with that.
It's probably Dan or Yuri a better place than me to the specifics, but we treat it as if we would, it's a detector PC. So we run an rsync off that for the frames, that then is passed into the general pipeline. Yeah, so I think Yuri is probably is adapting the pipeline for the Falcon 4. So he's probably best to comment on that. But we find the vast majority of stuff is on the K3s now anyway. So I think the pipeline still works in the Falcon 3, but it's been a while.
I guess that is an advantage of the kind of slightly hacky script way it's done at Diamond, that actually means every detector is treated the same as far as the processing goes. Everything is just new files coming into the Linux file system on disk, and you go from there. Of
course, and that's been crucial. You know, it was the K3 integration that was, you know, fantastic on Reliant and really useful in that respect. So obviously, yeah. So in Diamond is part of the IceByB collaboration. So we treat, you know, beamlines and detectors, try and treat them as universally as possible, and then have, you know, software that obviously, or syncing scripts that write to the cluster, and that the metadata is fairly universally accessible. But I'll let, Yuri and Dan are the experts on this, not me.
We treat it as the same data, but we need to experiment now. We've got a Tina server for one of the microscopes. We need to see how we can integrate that, and if there is any benefit in using this.
I just noticed there's a comment in the chat from a while ago from Andrea asking about possibly robocopy as an option for file transfer. So I guess Christian and Marcus, you both mentioned doing file transfers on Windows. Is robocopy something you've used or considered, or do you do this another way?
I mean, I can comment on that. It runs in the Windows PowerShell. It behaves pretty much like an rsync. You don't have to do any fancy scripting. It's quite powerful, so you can just copy files or move files. You can set how often you want it to check for new files. And yeah, we run it on both the K2 PC and the Falcon server. And we've had no issues with it. So I would highly recommend it.
And is that, again, just offloading files onto a network mounted storage drive?
Exactly. Yeah. So the machine needs to be, connected to either, the internet or your internal network so that it can see this external storage. And yeah, so far it keeps up with the collection. But again, we're not super obsessed with trying to keep up with every single movie. Like if it lags a bit, it's not the end of the world.
So I have another question for you. So normally all these automated pipelines, they concentrate on a single project, the one that is being acquired now. But I think it would be good to have a database with historical data so that you can compare how the microscope is working with respect to 6 months ago, for instance. What do you think of that?
What criteria would you use?
Yeah, I don't know, productivity or maybe number of micrographs per hour, or yeah, because all the rest they're very variable.
It's very difficult to call, because if something went wrong, the speed could be the same. But we recently found an issue. Basically, instrument someone of our users probably changed some settings, and a couple of sessions perhaps got affected. The speed was the same. It's just the microscope settings were different. Yes, potentially you can track it, but yeah, you can only see it if you didn't get resolution you intended to get, and this is pretty much sample dependent, so it's really tricky to evaluate. That's my view on it, but yeah, if someone suggests a good criterion, it would be interesting.
Yeah, Marcus, do you have your hand up? Go ahead.
Just on this point, I think what most important is that you have a good standard sample which you run on a regular basis, probably. I mean, I think a lot of places basically have a bit of April-13 running around. You know what you should be getting out of it. And I mean, nowadays collecting April-13 you can do within 2 hours, basically. And I think that at the moment seems to be the most valuable thing, I think, to know if your machine is still running as it should be.
Yeah, that's a very good point. Yeah, periodic benchmarking is crucial.
Totally agree on periodic benchmarking. I think we think is the only way to guarantee, to sort of say all the projects that were run in the week before this, the microscope should have been working because benchmarking says so. We had a lot of discussions about using people's dashboards, using all these kind of dashboards to determine what is a failed session, especially when money's changing hands because they want to play the blame game. The output of GCTF doesn't tell you this. It tells you you have really nice carbon. It might not tell you anything if you have a gold grid. So yeah, we spent a lot of time with contracts trying to work out what a failed session would be, and in the end, all we could say was we can point to the most recent benchmark. Dashboards tell you a lot about how the session's going, but not necessarily if the session's going badly. It doesn't tell you whose fault it is, microscope or sample.
Following on from that, on the software side alone, one of the things we're working on implementing at eBook at the moment is a kind of automatic periodic testing of the processing pipeline. So not running an actual microscope to collect any data, but just running a processing session to check that the cluster and all the associated things are still running properly. Is that something that anyone else does in their facilities, or anything people are interested in?
For the development, we find useful to simulate a session. So we also have scripts that generate data or copy data to some folder at some particular speed and so on, but just to make the development. But we haven't used it for testing the processing of the cluster or whatever. I agree that it is useful.
Yeah, it's probably something that we find particularly useful because of the way our sessions are structured. We have runs and shutdowns. So in our ideal world, which we're not currently in, obviously, at the end of every shutdown and at the start of every run, every microscope is benchmarked, and the entire cluster pipeline is benchmarked as well, prior to user data acquisition, obviously. I don't think we've successfully achieved that for every single microscope. Well, we haven't achieved that for every single microscope at the start of every run, but we'd like to move towards that. And I think it's clearly a very useful thing.
Yeah, I mean, I think it's one of the things, it's one of the reasons why we're trying to get the metadata from the pipeline into iSpy-B, so you do have a database so you can look at trends and things like that. On James's point, yeah, I mean, I agree, the CTF resolution is not necessarily the be-all and end-all. I know our industrial guys what they do if they have a problem trying to convince people is they take some shots of carbon next to the holes at the start of the session, show that the tone rings go out to X point, and so that's so what you see in the images, because it's obviously dependent on what you've got in your image. So, but yeah, I mean, there's always conversations about what metric to use. I mean, Sean Rawlinson yesterday showed in the main session, you know, that they found something through looking at the kind of average motion that they see in motion core, and that helped them diagnose a particular issue with their microscope. But again, you know, that's kind of a bit dependent on what you've got in your image. If you've not got much in the image, or you've got few particles, then your motion correction is probably not going to work that well.
Pascal's put a question in the chat just asking, how often do you benchmark? So, I think one or two people have already hinted at that, but if anyone else wants to come in on that, please go ahead.
Yeah, I mean, we have shut down, so I mean, we do regular checks. It is a bit boring, because, you know, there's only so many times you can solve apoferritin before you start to lose the will to live. But yeah, I mean, it is quite a useful object to have, as Marcus said. You know, I think 2 hours, that's a long session for apoferritin, isn't it? I mean, you can probably do that in a couple of micrographs these days, but yeah.
So I would say you should, I mean, we try, our runs are what, every month or two, but I would certainly, and it's quoting Hagen, but you know, running a benchmark after any major intervention on your microscope is not a bad idea.
So anyone else from any other facilities want to comment on this? I'm interested actually to hear how it's done at EMBL. I don't know, Felix, do you want to comment?
We are not running actually real benchmark. I mean, we just keep, so since we have a lot of internal sessions, many internal sessions, we keep an eye, because we can easily have some feedback within a couple of days, how things are going, and how, because in terms of single particle and tomography, and from time to time, yes, we have ribosome and apoferritin, but nothing clearly nicely scheduled. But at least for all internal sessions, we really try to keep tracks and keep an eye on feedbacks and stuff to see if they actually reach something good.
So we're getting towards the end of our time for the discussion. So that, just finished with a kind of looking a wider perspective. So where do you see the kind of processing pipelines and software going? Are there any kind of major long-term visions you think no one is addressing yet that we should be working towards as software developers?
So my vision is that there is all the time more and more automation and more automatic decisions taken on the data. And they are getting better. So at the end, at least up to the level of 2D classes and initial volume, I think the user could use whatever comes out from the facility directly.
My personal opinion on this is also that we should, you know, maybe separate what we want to do in the end, because of course, if you want to solve a tricky project, you always have to manually process and look at everything. But I think what the automatic processing can actually give as a very powerful output is an immediate feedback on a sample, like when you collect overnight on an initial data set, and you know the next morning what your sample looks like, you know how to plan your experiments for the next 2 weeks, for example. And for these kind of applications, I think all these automatic pipelines, they're actually extremely important for the biologists, not only for the facility, but for the biologists to actually make some progress quickly in their projects. And in the end, if you have a tricky project and you want to classify a lot, you have to do it manually, I think.
So are you saying there, Christian, that the kind of automatic classifications in the pipeline will be a major step in that direction? Or?
Yeah, because you have to make, you need to make decisions, and these decisions you probably cannot completely automate. That's at least my personal opinion. Of course, you can do an exhaustive classification and refining all kinds of combinations of classes and things. But in terms of computation, this is a bit unreasonable, I think. So for a tricky project, I think there still has to be some manual intervention. If there's something known, you can do supervised classifications. And this you can really nicely pipeline already nowadays with Relion, but yeah.
Yeah, at the level of 3D, I completely agree. At the level of 2D, you could do some automatic class selection, and normally they more or less work, even if they're not perfect.
So I tried Cinderella some time ago with 2D classes from CryoSpark, and it actually did an amazing job. So I was really surprised. I think I gave it like 10 or 15 sample data sets, and from this it was able to select 2D classes quite reliably. Good enough for, let's say, to automate everything to a 3D reconstruction automatically overnight for initial data set. Of course, if you want to have proper processing, you might want to also manually curate your 2D classes. But of course, it would be beneficial if this manual curation would not be necessary anymore.
And presumably in that case, the automatic 2D class selection at this point is mostly about just cleaning up the data set and removing the junk particles. And we're not yet at the point where you might be able to use that to actually do kind of classification between good particles and particles in different conformations, compositions, that kind of thing, which you might really care about in the long run.
Also depends on particle picker, because if you don't select a lot of junk, it depends. Sometimes you just cannot avoid this, but we found that we don't use 2D classification as a tool for selection of particles for 3D job. And some users who choosing to do this actually they selected preferred orientations. So if you have confidence in your initial particle selection, you can proceed straight to 3D analysis without need of 2D at all.
Yeah, just a quick comment about on-the-fly processing. So we're also running, and I guess many people are also running, external guests, so for high-end data collection. And one process to receive people is they need to apply and show preliminary data. So the good thing, maybe, I think those on-the-fly processing should be also actually even more important for screening microscope than actually for cryos, because many people, I think, agree that most of people collecting high-end data collection just like to have just raw TIFF files and process them on their own, in their own setup. But for screening microscope, it's completely different story. People most of the time just want some preliminary data, maybe nice statistics, CTF, resolution estimation, 2D classes, just to be able to fill for an application form to go to the EBIC or Diamond or Nissan or wherever. So to be honest, I mean, the on-the-fly processing with WAP on Cryos, on Cryos, it's just really to see if there is a bad square here and there. But we hardly use any of the input, maybe the particle picking, but most of the people actually rerun WAP and return WAP on their own data. For the Talos data, Arctica data, it's a completely different story. You just want the output as fast as possible in order to be able to know Cryos as fast as possible. Hence my question on Falcon 3, because Falcon 3, we have it on Arctica.
I could not agree more with you. This is exactly what we do. We run automatic pipelines on the screening microscope where we get initial data sets, and Cryos is only for monitoring that the microscope is not going bad.
Yeah, that's interesting. That's something I hadn't thought of before myself, certainly, but that makes a lot of sense that actually on the screening microscope is where you really want this kind of automated processing just to tell you if your grids are any good.
When you're running Cryos for hand data collection, yeah, in order to when people ask, for 1 day, 2 days, 3 days, 4 days of Cryos, I mean, if you have some already clear numbers, okay, that's my grid screen. I know have so many squares and so many particles. So probably with what I want to do pre-processing, I need maybe 500,000 particles. So according to this grid, 2 days should be largely enough with your throughput. That's the thing, because people, you offer the 5 days of Titan Cryos, they are super happy, but maybe 2 days would be largely enough, maybe with a bit more detailed pre-processed data or input, whatever.
I think in general, what Felix is saying over there is right, but I think it also heavily depends on what you define as a screening microscope. Not everybody has even a facility screening microscope with an Arctica.
So to apply, I mean, what you need to apply to Cryos facility, basically. I mean, you need at least in the INEX thing, because we at least ask for convincing 2D classes, bare minimum.
Yeah, but for example, people who are coming to us, we are having as a screen microscope Joule 1400s. And external people, at least in our country, they also don't have anything better than that as a screen microscope at hand. So we can ask for them 2D classes, but I've seen projects coming in here where it looked decent enough on a Joule 1400 with lab 6 filament. You put it into a cryo arm with energy filtering, you suddenly see how much more background noise they're actually having, because we suddenly start seeing this kind of stuff. So we had projects basically look perfect on the screening microscopes, and you could see the more we started collecting these things on the high-end instrument, it was still. So I think it's still valuable to have also these live data pipeline running on the high-end microscope, depending on how much quality information you have beforehand.
Yeah, it certainly sounds like no one is suggesting not running live processing on the high-end microscopes, but perhaps on the high-end microscopes it's more as a way of monitoring the performance of the microscope, and you expect that people are going to do their own detailed processing later to get the best out of their data. So thank you very much, everyone, for a very interesting discussion. Thanks to our panelists for their introductions and contributions, and I hope you've all found that useful and yeah, got up to date on what other people are thinking, and raises ideas you can go away and work with, and contacts you can talk to people about if you've heard something of interest.